Hello everyone, welcome back to the MOOCs course on Advanced Analytical Technique. We have started unit 2nd of this course and the topic that we are discussing is molecular luminescence spectroscopy. This is the last slide that we have ended our lecture with yesterday. And while discussing this slide, I was just explaining you in a nutshell about the Jablonski diagram, that we are having excitation through these blue lines, and then if they are coming back directly from excited singlet to ground singlet, it is fluorescence, while if they are if the electrons are undergoing a flip, but if the electrons are undergoing a flip, changing their spin state from excited singlet to excited triplet, and then they are coming back to ground singlet state, it is called as phosphorescence. You all know about it. And then these phenomena can be represented in the form of a spectrum like this. We have discussed this is the absorption spectrum, which is due to the excitation. This is excitation spectrum, which is due to the absorption, this one, while this is emission spectrum, and the distance between these two maxima is called as the Stokes shift. Let us start today's lecture with correlating the fluorescence intensity with factors like the intensity of the incident light radiation as well as the concentration. So the intensity of the fluorescence emission depends upon various factors. For example, the intensity of the light that is being absorbed by the sample causing excitation. The same has been presented here, that the radial power or the intensity of the fluorescence emission is proportional to the intensity of light that is being absorbed. And now how we are going to calculate the intensity of light being absorbed? Suppose P naught is the intensity of the incident light radiation, and if this P light of intensity P naught is passing through a sample, while some of the energy is absorbed, while the remaining light of intensity P is transmitted, where P is of course less than P naught, because some of the intensity is being absorbed, causing excitation of electron to the next level, so that when electron comes, they emit light radiation causing the phenomena of fluorescence. Since some of the light is absorbed, the light that is being transmitted is having an intensity of P which is lesser than the incident radiation's intensity P naught. Now in order to calculate the amount of light absorbed, we can use P naught minus P. So P naught minus P, suppose, gives us the amount of light absorbed or the amount of power that is being transmitted into the electron by the absorption of that particular light radiation. So we can say that this fluorescence intensity is proportional to the difference in the light radiation of the incident light as well as the transmitted light, because this difference gives us the amount of light that is being absorbed for excitation. P naught is the intensity of incident radiation, while P is the intensity of transmitted light. Although we have nothing to do with transmitted light, I have explained you yesterday that even we do not want this transmitted light to reach to the detector, and that is why in case of fluorescence spectroscopy we always keep the detector at 90 degree. Here we never put the detector here, because if it is placed in a straight line, it will always have some transmitted light causing current because of that transmitted light, which is not fluorescence. So in order to calculate the fluorescence intensity only, we always put the detector at 90 degree to the sample, so that it will capture only the fluorescence emission, because they are emitted in all directions. The intensity of this light also depends. This is some calculation that I am going to explain you just now. The intensity of this fluorescence light also depends upon the concentration. So there are two parameters. One is the concentration on which the intensity of this fluorescence light depends, and then there is another parameter, the difference in the intensity of the light radiation. Then there is one, the fluorescence intensity also depends upon the concentration of the sample that is being under analysis. So there are two factors on which the fluorescence intensity depends. It depends upon the intensity of the light which is being absorbed, and this intensity is calculated by taking a difference between the P naught and P. P naught is the intensity of incident radiation, while P is the intensity of transmitted radiation, and it also depends upon the concentration of the species, because if the concentration is high, of course there will be more interaction, there will be more molecules in the pathway of the light radiation, and there will, when there is more interaction, of course the absorption of light will be more. So when we remove the proportionality sign, we put a constant k. So this is the equation. So this is the equation which relates the intensity of fluorescence with the intensity of light absorbed as well as the concentration of the sample. So C is the concentration of the sample and K is the proportionality constant. Now upon further solving this particular equation, we have some more conceptual representation of the intensity of fluorescence light. In one case, we can have this intensity of fluorescence light is equal to Ki naught epsilon C L and phi, where phi is the quantum yield, which is defined as the ratio of intensity of fluorescence light or ratio of intensity of emitted light to the intensity of absorbed light. Also, I explained you yesterday that there is a term internal quantum efficiency, which means that total number of electrons that are excited upon absorption of one light ray photon. And then there is another term, photoconducive gain. Photoconducive gain defines the increase in the current upon absorption of one single light photon. But the quantum yield in this particular case is defined as the ratio of the intensity of fluorescent light to the intensity of absorbed light. Now how this formula will, now how this equation has been evolved. I hope you remember about the Beer-Lambert's law. This is a very famous law, the Beer-Lambert's law in UV spectroscopy. This law states that the decrease in intensity of the light radiation when it is passing through the sample with respect to thickness depends upon, means it is proportional to the intensity of light radiation itself as well as concentration. If we rearrange this equation, we may have minus di upon dx is equal to k I and c. This is the same calculation that I have made in this presentation. I am showing you again. Now if we rearrange this equation, here we have removed the proportionality sign and we placed a constant k, proportionality constant. Now if we rearrange this equation, it is minus di upon I is equal to minus k c dx. Upon integrating this equation, we get, so if we integrate this equation, we get minus log I equals to minus k c and x, and if we are integrating it within the limit I naught to I, so here we put I and here we put I naught, then this will become log, and there is a minus sign as well, so log I upon log I minus it is natural log ln I naught is equal to minus will go minus, there is a minus sign as well, so it minus k c and x, it will become I upon I naught, because log a minus log b is equal to log a upon b, minus k c and x. If we remove the log here, the other term will go to the power of e. So I will be equals to I naught e to the power minus k c x. If intensity is represented by p instead of I, the equation will be p is equal to p naught e to the power minus k c and x. Now since we have this equation and p is equal to p naught e to the power minus k c x, putting this value of p from here, this f will become k p naught minus p, and this p is equal to p naught e to the power minus k c x, and then we have this term c. F will be equal to, if we take p common, p naught common, 1 minus e to the power minus k c x into c. Now at low concentration, we get this form k p naught e c x, and we put phi also because it shows the quantum yield. Quantum yield is basically always lesser than 1, which means that not all the light that is being absorbed is converted into fluorescent light. Some of the light has always been lost, and that is why we get Stokes shift. If the light is completely transformed into fluorescent light, means the energy of the light that is being absorbed, or the intensity of light that is being absorbed, is 100% transformed into fluorescence, then the value of phi or quantum yield will be 1, and it never happens. Otherwise, the peak position of absorption or excitation and emission will be same, and Stokes shifts will be 0. And I told you that this is not the case with fluorescence. There is always a positive value of Stokes shifts in case of fluorescence. So this is a more conceptual equation correlating the intensity of fluorescent light F with the intensity of incident radiation represented by I naught, or sometimes it is represented by P naught, and this equation also relates the intensity of fluorescence light with the concentration C, the quantum yield phi, molar absorptivity, as well as the power of the incident radiation P naught or intensity of incident radiation I naught. Both are same. So when we plot a graph of fluorescence intensity with analyte concentration, for example, we have a sample and we prepare different dilutions of this sample, thereby changing its concentration. So suppose we have 1 ppm here, then we have 2 ppm, 3 ppm, and like this. Just like in this case, we have our solution has been analyzed by fluorescence, and the solution and the solutions belongs to same sample, only the concentration is different. So it is 1 milligram per ml. 1 milligram per ml is very high concentration, because 1 milligram per ml, if we can multiply it with 1000, it will be 1000 milligram per 1000 ml, which means 1000 milligram, and 1000 ml is 1 liter per liter, which is equal to 1000 ppm. So it is very high concentration. So it is quite a high concentration. So if we plot a graph between the fluorescence intensity as well as the concentration of the samples, it will come like this. It will come like this. In this graph, you can observe that till this point, or more correctly I should say till this point, if we can see, this line is straight, while from this particular point the graph is getting deviated from this straight line, and it is changing its position, and finally it becomes almost constant. This shows that at low concentration, the fluorescence intensity F is proportional to C. There is a direct correlation. If we increase the concentration, fluorescence intensity will go up, but it happens up to a certain concentration limit. Beyond that concentration, this equation does not hold good. Here it is following linearity, but then it becomes non-linear. So At low concentration, we have a linear relation between the fluorescence intensity and concentration. As the concentration goes beyond a particular value, the fluorescence intensity does not increase correspondingly, and at a certain point it becomes almost constant. Especially this particular region, you can see it is getting constant, and if we keeps on increasing the concentration to 7 and 8, it will become constant. So this this graph shows that, this plot shows that at low concentration we have a direct correlation, and they follow the principle of linearity, the fluorescence intensity and concentration. But as the concentration goes up, it deviates from the linearity, it becomes non-linear. Now the constant K that is being used in the equation on the previous page, we have this equation, and we also have a conceptual form where we have K I naught epsilon C L and phi. So this proportionality constant K depends upon several factors. The first factor is the intensity of incident radiation itself. This constant K depends upon the intensity of fluorescence radiation. So K is proportional to P naught. Now, in order to enhance the intensity of fluorescence emission, what we should do? The first thing, we should use a light radiation of high intensity. The intensity of the incident light should be high, the first thing. Because if the intensity of light radiation is high, and since fluorescence intensity depends upon it directly, it is directly proportional, it means that the chances of fluorescence emission would be high. Further, if the absorptivity means this epsilon, or sometimes if this epsilon is represented by small a, because we have another formula for absorption which is being used in UV spectroscopy, absorbance is equal to ABC, or sometimes it is written as epsilon BC, where B is the path length, C is concentration, and this is molar absorptivity. Molar absorptivity is the absorption by 1 mole of the sample, and it depends upon the sample. It is intrinsic property, it depends upon the type of sample. In case some samples have high molar absorptivity while some have low molar absorptivity, it depends, basically it depends upon the presence of fluorophore in the sample. So in order to increase the intensity of fluorescence radiation, we must take a higher value of P naught, means the intensity of incident light should be high. Further, the sample should have high molar absorptivity, it will increase the chances of fluorescence emission, and the path length should also be good enough. This L in this equation represents the path length. Here in this equation B represents the path length. Path length refers to the path length if the cuvette is placed like this, or if the cuvette is placed like this, it is basically the thickness of the cuvette, or in this way it is the distance the light travels while passing through the sample. If this distance is long enough, the light radiation would have more time with samples to interact, and there will be more number of molecules also that will come in on its way for interaction, causing absorption. With high thickness, then of course when light passes through this particular cuvette, there will be more number of molecules present along its path, interaction would be more, and ultimately the absorption would be more, resulting into higher intensity of the fluorescence light. Again, the quantum yield that I have already explained you, the quantum K, the constant K also depends upon the quantum efficiency. So this K depends upon intensity of the incident light, maybe P0, or it may be represented as I naught. Clear? This K also depends upon, because if K increases, the chances of, if K increases, F increases. So if we take a sample with high molar absorptivity epsilon or A, and if we take the thickness of the cuvette high, so B or the path length, if it is represented by L, should be high. These parameters are directly affecting the constant K, and then the last parameter that influences the constant is the quantum yield, represented by this letter phi. The formula is given here. Quantum efficiency phi is equal to intensity of fluorescence upon intensity of absorption. So it is a ratio of the intensity of fluorescence to the intensity of absorbance, and the value of phi is always lesser than 1, because in no case the intensity of light absorbed is 100% converted into the intensity of light emitted through fluorescence, because when this light intensity is absorbed, causing the sample to excite, some of the light radiations are being lost in the form of non-radiative energy loss via heat or kinetic energy due to vibrational relaxations or due to quenching, and the remaining energy only is emitted when the electron comes back. I have explained you these phenomena of quenching and vibrational relaxation when I was explaining the Jablonski diagram in detail. There I have shown you these types of lines which basically represents the vibrational relaxations, because in the ground electronic state also there are certain vibrational levels, and in the excited electronic state also there are certain vibrational levels. So if the electron is traveling from ground state to excited state, and it travels some vibrational levels as well, it comes from higher vibrational level to the lower vibrational level, which is called as vibrational relaxation. It causes loss of energy in the form of heat, a type of non-radiative energy loss. So this loss causes the intensity of the final fluorescence emission to be lower than the intensity of incident radiation, and then sometimes quenching also occurs, which is also a type of non-radiative energy loss. So these phenomena reduces the intensity of fluorescence light emission, and therefore the value of phi is always lesser than 1. These are the few factors that affect the intensity of the fluorescence light: quenching, the temperature of the sample, conjugation in the sample if present or not, the pH of the system, as well as the concentration of the samples. So these are the factors that I am going to discuss with you, and that directly affects the intensity of the fluorescence light being emitted. As you all know that quenching refers to the loss of the intensity of light due to a non-radiative deactivation or non-radiative energy loss, and this happens because of some quencher that is present in the sample that has been deliberately added, or that is present in the form of an impurity, and this quencher reacts with the excited state. Excited state is always represented by a symbol star. So if A is in excited state showing fluorescence, and if there is a quencher present, it will immediately becomes excited, takes the energy from A, while A gets deactivated, and in this process, since it is non-radiative, no light is emitted, and the intensity of fluorescence is reduced, or sometimes it is completely vanished. So this is called as quenching. So quenching always reduces the intensity of the fluorescence emission. Then temperature means, for example, if the temperature of the sample is high, then that means more number of molecules are colliding with each other, because temperature is directly related to the kinetic energy of the molecules. If temperature is low, the kinetic energy is low, which means that molecules are moving at slow speed, and if at that speed the chances of collision are low, and if the collision happens, since the kinetic energy is low, the impact of those collisions is very low, and therefore it will not cause any quenching, or it will not cause any non-radiative loss. It will not affect the fluorescence intensity. But if the temperature of the system is high, then of course there will be molecules which are moving at very fast speed, and at that fast speed, if they are colliding, then it will create a significant impact, transferring their energy, thereby reducing the intensity, and it causes the molecules to deactivate. It will causes a molecule which is excited to come back to the ground state, and in this case also no light is emitted, only the energy is transferred from one molecule to the other molecule. Then conjugation. Molecule must have conjugation. Yesterday also I told you that presence of aromatic ring is a very good thing for fluorescence to occur. Most of the fluorescent molecules are aromatic in nature. So if a sample is aromatic and if the conjugation is so if the sample is aromatic, of course there are chances that it will show fluorescence, and if in that aromatic ring the fluorescence also depends upon the number of rings as well as the conjugation. So if we have more conjugation, the electrons due to this conjugation are delocalized. These electrons can move freely, and these freely moving electrons can be excited easily to the excited state, and when they come back they emit light radiation in the form of fluorescent light. So conjugation is directly proportional to the fluorescence intensity. If we have conjugation in the system, it will of course increase the intensity of the fluorescence light, and because and this conjugation causes resonance structure, and resonance stabilizes the excited state. For example, in case of aniline, this is a molecule of aniline, and we have a lone pair of electron on nitrogen. When this lone pair is involved in the process of fluorescence, like this, it forms a double bond, and then the lone pair will come over here and we have a double bond, and in this way these electrons are delocalized, means the excited state, and delocalization on resonance means the molecules loses some energy due to this resonance structure, and therefore it is stabilized. Now since the molecule is stabilized, the electrons can be easily excited by absorption of light energy, and when they come back they emit light radiations of longer wavelength, means the visible light, and thus they show the phenomena of fluorescence. So the molecule must have conjugation, and as the conjugation increases, the fluorescence intensity increases, because conjugation causes electrons to flow freely, and those electrons can be very easily excited by absorption of energy, and this conjugation stabilizes the molecule because of the phenomena of resonance. Then comes the pH of the system. pH has some complicated effect on the phenomena of fluorescence, but in general we say that pH increase causes the fluorescence intensity to go up. Clear? And in case of acidic samples or samples with lower pH, there has been some quenching. The intensity of the fluorescence light decreases. Why? Because for example, if you have a sample which has a lone pair of electron, just in case of, for example, we have this particular case, we have a lone pair of electron. If it is present in an acid, acid will donate its proton, it will form this species, because under acidic condition the proton is being released by an acid, and which is taken up by the non-bonded electron pair. For example, in this particular case, since aniline has a lone pair of electron, and if the solution is acidic, it will release proton. That proton approaches to the non-bonded electron pair, making it like this, converting this molecule into this particular form. Now the electron pair is not free to move, giving the phenomena of resonance, and since it is not involved in the phenomena of resonance, it is not moving at all, it is stick to its place, then that means there will be no fluorescence in this particular case. So a low pH value means an acidic solution reduces the intensity of fluorescence light, although in some cases, even in basic solutions also, we have a lower fluorescence intensity. So the effect of pH is a little bit complicated, but in general we can say that up to a certain limit, in acidic conditions we have a lower intensity of fluorescence, and as the pH goes up, means we are moving towards basic solutions, the intensity goes up. The same has been represented in this diagram. Here you can see that we are changing the pH of a solution, and the fluorescence intensity, although it decreases initially, but in all cases the fluorescence intensity is increasing as we are moving from lower pH to higher pH, as we are moving from acidic solution to alkaline solution, the intensity of the fluorescence is going up. In this particular case, we have used 2 millimolar concentration, and the excitation of this surfactant means the absorption of light happens at 515 nanometer, while the emission, because emission always occurs at longer wavelength, it is always towards the right hand side. So emission occurs at 570 nanometers. So there is a difference in the intensity of 55 nanometers. The stroke shift is 55 nanometers, and in this particular case of surfactant of 2 millimolar concentration, the effect of pH has been represented as the acidic solutions have lower fluorescence intensity, while as we move towards higher pH from lower pH value, as we are moving towards basic solutions, the intensity of the fluorescence is going up. This is again the same formula that I have derived in the previous case, the effect of concentration, and it shows that fluorescence is directly proportional to concentration, but since I have shown you a graph as well, this equation holds good at lower concentration only, because if we increase the concentration at high concentration, the graph moves away from linearity, it becomes non-linear, while at low concentration it is linear, means fluorescence intensity is directly proportional to concentration. So we can say that just like pH, we have a little bit complicated effect of concentration on fluorescence intensity. At lower concentrations, means for dilute solution, the fluorescence is directly proportional to the concentration. We have a linear relation. As we keeps on increasing concentration, there will be a corresponding increase in the fluorescence intensity, but after a particular value of concentration, there has been some deviation from this linearity, and at very high concentration, this plot becomes almost parallel to x-axis, means when the concentration becomes very high, there will be no increase in intensity, and sometimes due to high concentration there will be some sort of quenching, and the intensity of fluorescence decreases at very high concentration. The same can be represented in this graph. Here you can see that at lower concentration the line is straight, which means that up to 200 milligram or 300 milligram per liter, means up to 300 ppm concentration of the sample, we are having a linear relation where fluorescence is proportional to C, its concentration. But as the concentration goes up to 400 ppm, 600 and 800, the graph is moving away from linearity, and the intensity is not correspondingly increased with increasing concentration, and at 800 it becomes almost constant. And as I said that at very high concentration the molecules collide with each other, the number of collisions increases, and thereby the intensity of fluorescence decreases due to quenching. And the same is represented here, that at 1000 ppm, means 1 gram per liter, 1000 milligram per liter, the concentration is so high that in this particular case, that because it is the fluorescence of crude oil, so at very high concentration of crude oil there are collision between the molecules, and therefore the fluorescence intensity decreases, means self quenching is taking place. So this is all about the effect of different factors on fluorescence intensity. In the next slide we will discuss some more details of the phenomena of fluorescence. Till then, thank you very much.